And I would like to introduce you Vuksan, who came from Serbia as well. He's the lead backend developer from GameCredits.
Yeah.
And he will give you the brief introduction into blockchain, into mining process, and he will show examples using Python about how to do it. So please give a warm welcome to Vuksan.
Okay, I guess right now all of you know what mining is because Nicola introduced it. So I will just show you how it really works in the end, under the hood. So before we can actually explain the mining process itself, we need first to cover some terminology for the people who are not blockchain developers or something like that. So what is blockchain? Blockchain is a public, digital, and decentralized ledger of transactions. So this ledger, by its structure, Bitcoin is actually a backlinked list of blocks. So it consists simply. It looks. I hope that at least some of you can see this because I didn't think I really need this board. So in order to explain what is a block is the container for the transactions. So each block is identified by its block hash. This is just, let's write it down. And this block contains multiple transactions. And so on. So what is a transaction? A transaction, I mean, everyone knows it's a transfer of value from a person A to person B, and in the blockchain, a person is represented by its address. So in order to come to that, I need to explain what a private key is. And so a private key is the only thing that you need in order to send the Bitcoin. It's a way. The private key is what makes you owner of funds. So what do we need to create this private key? Well, we actually don't even need a PC. We only need a piece of paper, a dice, a coin, and a pen, of course, to write it down. So you can flip this coin 256 times, actually, and then write down ones and zeros. Heads, there is one, tail zero, for instance. And let's say you will get a unique private key. Well, it will be in bits, of course. So you would need to translate it into hash, and that is actually the only thing you need in order to be able to create transactions. You don't even need to have an internet connection. So right now, okay, we can send the Bitcoin, but we don't have it yet. So in order to receive it, we could actually receive it also on this private key, but the problem is that if we show this private key to anyone, they immediately become the owners of our money. So in order to do that, we need the public key. Most of you are probably familiar with this because this is the public and private key encryption, actually, and it's an old terminology. So public key is actually a one-way function, hash function, which hashes the private key. Okay, I will write down the bigger letters. I call private, and hash of this private actually gives public key. And this is a one-way function. Hash functions cannot be reversed. So if you know someone's public key, there is no way for you to get this private key. So right now, if we have a public key, we could also show it to anyone, and anyone can send the money to us, and there is no danger that our funds will be lost or stolen by anyone. So the next concept is finally the address. The address is just a simpler way to show someone this public key, because this public key is pretty long and it doesn't give any information. The address, when you see the address, you can already know if it's a Bitcoin address or some other cryptocurrency address, because Bitcoin address starts with 1. So whenever I see an address, I know if it is in Bitcoin or, for instance, GameCredits address starts with G. So that's about basic terminology. So we can move to actual Bitcoin network. What is Bitcoin network? Bitcoin network is peer-to-peer digital network that sends those transactions. It is consisted of nodes. Node is basically a computer or a device in this network, and that actually sends and resends those transactions, validates them, and so on. You will see in a couple of minutes. And next important thing to know is that there are several types of nodes. First type is the full node. The full nodes are the nodes, the PCs that have the whole history of the blockchain written in its database. So that they are the independent nodes. They can work without any other node that provides information to them. And apart from those full nodes who have all the information, there are lightweight nodes, because currently Bitcoin blockchain, that database is like 100 gigabits large. So if you wanted to actually use Bitcoin, it would be hard to download it with slow connection and whatnot. So there is an option to have a lightweight node, which actually doesn't hold all the data, but only data that is important to you. So, and it connects to the full node, which it actually trusts that is doing a valid job and not cheating it, to get some information. And the last node type is the mining node, which is usually a full node. It doesn't have to be, but it usually is, and it has all the blockchain data in its database, and it also mines. It confirms those transactions actually and validates them. So,
sorry, Vuksan,
yeah?
one second. In case anyone has a question
Yeah,
at any
yeah.
point, just raise your hand.
Yeah.
He'll notice,
Yeah.
and you can interrupt him at some
Yeah.
point.
Because
So
it's
we
important.
can also-
I believe you
because it's a
may
lot of stuff.
may have some questions, because this is technical, and if we save it for the end of the presentation, you might be confused in the meantime. So, if anyone has any questions, just raise your hand. So, so let's talk about the thing that actually made this whole Bitcoin thing special. It's the decentralized consensus. Basically, so far we only had, well, mostly centralized systems, which is like the way banks work right now. It is you have one central peer, let's call it that way, that holds all the data, and that this is the center of trust. And we all, when we interact with the bank, we all connect to it, and we trust the bank's system. So in a way, you when you have money in a bank, you really aren't the owner of your own money. Because if the banks want it so, it can forbid you from spending your own money. Well, in the blockchain, this changes, because in the blockchain, this whole concept of trust is decentralized, and everyone is equal. So if there is no way for any node or any part of network to forbid some nodes to spend its money. So this decentralized consensus is what actually Satoshi Nakamoto invented, and what is the good thing about Bitcoin? So in the beginning, about blockchain as well. So how do we actually achieve this decentralized consensus? And yeah, I forgot to mention that this decentralized consensus is so okay. Now we have like couple of nodes. So they all have the blockchain, whole blockchain. Let's say that all of them are full nodes, and they all have full blockchain. But how do they actually sync? You know, how can it be that this node has all the data and this node has all the data, and they all believe each other? They all believe the network, that there isn't one node that says, okay, every transaction is sent to me, so I'm the owner of all the funds. This is done by the emergence of the decentralized consensus, and it actually, how do they achieve this decentralized consensus? Is by the interaction of those four processes, and I will explain each of them in details later, but for now I can tell you something about them. It's the first one is the verification of transactions, where actually transactions become, or let's just go up front and I will explain them. So verification of transactions. Before each transaction is actually created in the beginning, let's say we have a girl named Anne and we have a guy named Peter, and Anne wants to send transaction to him. She first creates transaction in her wallet. So what the next step is, her wallet is distributing this transaction to the nodes across to its peers firstly, and then those peers distribute it across the network. And each of those peers actually first verify if this is a valid transaction, even before it is added to the blockchain. So that if this was an invalid transaction, it would reject it immediately, and even it wouldn't even come into the process of mining. So this is important because this way we have a first line clearage of transactions. So after our transaction hopefully passes this first verification step, we come to the aggregation of transactions, and this is something that all nodes do. When a node receives a transaction, and it is unconfirmed transaction, it's a new one in the blockchain, it puts it into a pool of unconfirmed transactions. So this pool is actually called transaction or memory pool. So what the miner does when he wants to actually mine a new block, well, first, if he receives the new block, he immediately starts the process of mining as soon as he receives the new block. So he gets the new block, he's like, okay, I can start the process of mining the new one. And what he does is that he creates a new empty node. I will just need a little bit of board for this. So he creates a new block. In this block, he puts all of those transactions, or most of them, and then one additional transaction. This additional transaction is called Coinbase transaction. And what is this transaction? It is a way for a miner to pay the reward of mining to himself. So a miner, because why do miners even mine nodes? Because there is a reward for them. There is like, if you successfully mine a block right now in the blockchain, the reward is 12.5 bitcoins plus all the transaction fees from all those transactions that client sent. So the reward is pretty big because Bitcoin right now is $8K. So you probably heard about Bitcoin mining farms and whatnot. So that's the incentive way for them to actually do all this heavy lifting for the network. So when they are creating Coinbase transaction, they put all transactions. They put the Coinbase transaction first into the block. They put all other transactions inside, and this is called candidate block. It is called the candidate block because it is not yet on the blockchain. It is not a valid block, but it is something that might be on a blockchain. That's why it's called the candidate block. So the next thing that he needs to do in order for this block to actually start, in order to start the process of mining, is to create a header for this block. What does this header contain? It contains a version, which isn't that important. It's just something that they use for protocol upgrades. It contains a previous block hash. What is a previous block hash? It is a way you need to append this to this chain of blocks. So you need to get the latest block that you know of, and you write it down here. So this transaction can actually append up here if you successfully mine it. So this block can actually append up here if you successfully mine it. So that's the previous block hash. What is Merkle root? Okay, so in order to explain Merkle root, okay, let's just put it down here. A Merkle root is okay. Let me tell you like this. This block right here contains 1,000. So it can contain up to 2,000 transactions. So if you actually make this block and append it to blockchain, where is the security that the miner or anyone later won't come and just change one parameter, one transaction that says it isn't sent to N or anyone else, it's sent to me directly. Well, in order to do that, we need to have a Merkle root in the block header, and this Merkle root is actually this. For each the transaction, we get its ID. So if we had, let's say, 4 transactions, we will have 4 transaction IDs. I will just call them A, B, C, and D. I don't know if you're familiar with the concept of Merkle root 3 because it's an older concept as well. So we have 4 transactions, and what we actually do is this: we hash each of those transaction data into the node. So those are the hashes. This is hash of an A, of a transaction data. So in order for us, we don't want, if we had 2,000 transactions, it would be 2,000 hashes of transactions. So we don't want to put 2,000 hashes inside of this because that would be very troublesome for the network, and that this would make a block very big. So in order for us to low it down, we make a tree. Here we make a new, let's say, node of this tree where we hash these hashes of A plus B. Because you know that when for a hash transaction you can input any amount of data into it, and it will always be, at least for SHA-256, it will always be 32 bytes long. So here we hash A plus B, here we hash C plus D, and finally in the root we have one hash of all of those transactions under it. So if we have a hash of all of these transactions under it, if you change a single parameter in the bit transaction, this hash will change completely. That's the point of the hashes, of the hash functions. So we store only this hash in the block header. So that's the Merkle root actually. The timestamp is only a time when this transaction is good. Yeah.
Regarding the Merkle root,
yeah.
Why not just concatenate all data of transaction and make like just one hash of that?
Well, you can also make that, but this is
Repeat the question.
Oh, okay. The question was why you don't concatenate all the data of all transactions and only do a hash of that. Well, I'm not sure why they didn't do it that way, because that would also produce. That would also produce the same result. Basically, not the same result. It would be a bit different, but it could work that way. But it works in this way because in this way there might be a way for you. I'm not actually sure. I could check that and answer you. You will get my email on the network about that, really, because that's an interesting question. So I'm not actually sure. I know that this is done this way, but yeah, someone else had the question.
Can I answer in terms of you?
Yeah.
Because the reason is quite simple.
Yeah.
Okay.
Baba.
The Merkle root is there because of easier updating. If you add some new transaction to the block, and you compute a hash from concatenate transaction, you need to rehash the all the transaction in the block. If you make some change, but in the Merkle root, you need only to hash the transaction which are on the path from your new transaction to Merkle root. I don't know if it's understandable, because it's better if I show it on table. But the simple answer is that in Merkle tree you can make faster updates than in normal sequence hash.
Yeah, well, yeah, that is actually true. But the main point is, because the miner, when he starts building this Merkle tree, okay, I'm not actually sure if he starts building this Merkle tree when he has all the pool of transactions and he starts building the block. So if it is that way, then he already has all the data he needs, so there won't be any new data coming. But if he doesn't, maybe it's true that he starts as soon as he gets the first transaction, so then that would be an answer. So okay, we can go on the timestamp, and so this is the only thing that you need to understand is that this Merkle root is the way for him to know that if any transaction changed in an easy way, that you can do this with any data. If you need to validate any data, you just hash it, and then you check this hash. And if anyone changes anything, any byte in this data, you will notice it immediately in the hash if you hash it again. So that's the way they check if the transaction is changed or not. So we've done the timestamp. The target is actually the difficulty. It relates to the difficulty of mining, which I will cover later. And the nonce is also the integer that the miner increases in order to mine. That will also be covered later. So after this block header is constructed, this is the later, yeah. After this block header is constructed, the mining process can actually begin. So what is mining? Mining is a process of adding those transactions to the blockchain. So what is the purpose? People get confused sometimes about purpose of mining. They think that mining was invented to actually make new coins, to introduce new coins to the network, because new coins come in this way because those 12.5 coins that miner actually receives are the new coins in the network. This is the first transaction of them. He gives them to himself. That's their beginning. So, but this is not really the purpose of mining. That's the incentive of mining. But the real purpose of mining is that the mining is actually the way that makes Bitcoin special. It's the way that makes Bitcoin secure, and it does so by the proof of work. So in order for me to simply explain proof of work to you, I would use an analogy with throwing dice. Let's say if I knew that you wouldn't lie to me by throwing dice, I can tell you, throw a dice until you get 12. You can get a 12 by only, at least 12, you can get a 12 by only rolling double sixes. So in order to get those double sixes, you would need on average, 33 tries or something like that, about 30 tries, I believe. So in order to get those 30 tries, when you come to me, or when I see after a while, I have you on tape or whatever, and when I see that you actually threw 2 double sixes, I can be sure that you made some work in order for this to happen. Because there is no way for you to throw a dice, actually, and make it happen for it to be, a regular dice is not those ones, that people use sometimes in tournaments, which isn't fair. So I know that you invested some work into it. So this is a way that mining actually works. I will show you. It's probably better if I show you in algorithm. And I already covered the rewards for mining. That's the incentive for the miner to actually do all of this work that I will now show you in my code. So okay, or we can do the board again, I guess, a little bit, and then I will show you just how it works and how hard it currently is. So what is a mining? You have all this data that is in the block header. You remember the version plus we can even go back and have version, previous block hash, Merkle root, timestamp, target, and also nonce, which is important. And you hash all of this. And you get some hash. Let's say, I don't know, whatever. And this nonce, in the beginning of mining process, miner initializes to none. To 0, sorry. So how does a mining works? Miner needs to get a hash of a block that starts with several zeros. So in order for him to do this, he needs to simply do the brute force. There is no other way. There is no other way for a miner to know what this nonce needs to be before trying for millions of times. Because what he actually does, this is how actual algorithm works, is that he tries first, and okay, he got this 0x1 whatever. He has, okay, I need to get something that starts like this. So he tries first time, he gets this. Okay, he says, okay, this is not it. Let's increment the nonce. Nonce is now 1. He gets this 0x, AB, whatever, 1, 3. He says, okay, this is not it. Increment the nonce to 2, and so on. And when he comes to some nonce, he will get a transaction that actually starts with 3 zeros, a hash which starts with 3 zeros, and it follows some things, and this is the valid hash of a block. This is the block hash that he's getting by hashing all of this. And the block hash is, if you remember from the beginning, what identifies the block. So, so for him, so I hope that everyone understood this algorithm, because it's actually pure brute force. You're trying to get hash that looks in a certain way, and the only way to do this is by changing one parameter numerous times until you actually hit the jackpot. So I have a simple program that does this in Python. It is very, very simplified. This isn't how mining really works in practice, but it is pretty much like this. I only simplified it for the explanation things. So here we have a candidate block. Remember, this is the block that isn't valid, that just has some things. So here I only put in this previous block hash, timestamp, and the target. It would be the same. I could put in version, but it's not important for this demonstration. So what does the mined block has that the unmined block doesn't? It has the also it has the nonce, and it has the block hash. The nonce is that valid nonce that it mined, and the block hash is actually what identifies it. So in order to mine this is the main functionality of this. This is the way that mining works. So we take this previous block hash, we take the timestamp, and we take the nonce. Nonce is 0 in the beginning, you see. So we try to mine. Here we have the mined transaction, and what our mined does is it only compares, you see, if the block hash actually starts with the target. Target is number of zeros. You see up here, target is like 3 zeros, and our block hash, if it starts with 3 zeros, it is true. If it doesn't, it's false. So it isn't mined until it starts with 3 zeros. So I would like to show you how this actually works by running this script. So let's see where it is. Okay. So we will run a miner. It will ask us to enter a target, because right now we are setting the difficulty of the mining process, and let's set it something easy for the beginning. Let's say 4 zeros. Okay, it found a new block. You see the block hash, it starts with 4 zeros, and the time it took was 0 seconds, basically less under 1 second. So let's try again, but with something more difficult. Let's try with 5 zeros. This should be over fast. Really. Yeah, there it is. So it took it 8 seconds for this. But what I want to show you is how this grows exponentially. It isn't something now. If we try it with 6 zeros, now it will probably take it a couple of minutes. We can go back to the presentation, and then I will show you, and then I will run it one more time, probably for 7 zeros, and that will be it. We cannot sit here for 2 days. So, because right now for the mining process, I'm using my MacBook, and my MacBook, in the mining terms, is a very, very, very shitty computer, piece of hardware. And the actual current difficulty or target for the Bitcoin starts with 18 zeros, and you will see how long it takes us to get. It will take us around half an hour to get 7 zeros. So for 8 zeros, you won't be here when that finishes, and for 9 zeros, I will probably terminate it tomorrow or something because it would just annoy me. So, okay, we can go back to the presentation. So, this was the process of mining. And now we come to the validation of a new block. Once the miner actually mines this new block, what he does is, yeah, do you have a question? No, okay, sorry.
No, okay, there is question from
okay.
YouTube actually.
Okay.
Which question is it? This one. Why we need 0, 0 at the beginning of each block? Can you explain?
Well, why we need a 0 in the beginning of the block? Because this is the way we need it.
I guess it means like, why do you start with zeros, not with some other characters?
No, it's just a way for we could, if it's just an agreement. You could start with ones, let's say, but they decided to go with zeros. I never met Satoshi Nakamoto to ask him this actually. So.
Okay. Okay, so when they add difficulty, they just add zeros at the beginning.
Well, yeah, this is a simplified way of doing it because difficulty is related to the target. Difficulty is there to make it human readable. So because when you say difficulty, you can say in terms of, let's say, hashes or how much hashes it takes you. But when you say target, this is what actual algorithm is checking actually. So that's why I wanted to show you the target and not the difficulty, because I can speak to you about hashes or whatnot, and it would be abstract for you. So after our block is actually mined, as soon as our miner notices that he mined a block, he will immediately relate to the network because he is the winner. So the first peer that gets this mined block and every other peer will check if this is actually a valid block, because if we didn't check this, miners would have a way to cheat, you know, and the most important thing is that checking of this doesn't take any time. The checking is actually done immediately, and the way to check is because you remember that in our valid block, we have a mined block, we have a nonce that is set to some value that miner used actually to mine this. So what those nodes need to do is take this nonce and just do one hash. They put this nonce here, and they check whatever it is, and they check if this hash is the hash that miner got, and if it's a valid hash, if it starts with the zeros, and that's it. And it is done immediately, and they can check it immediately, but for a miner it takes some time to do it. So this is the way validation of a new block works, and once this new block is on the network, it gets appended to the chain. And by appending to the chain, the miner extends the main chain. But there is maybe some of you see some problem with this because this network is huge. And what happens, you know, that when you are sending a message over a network, there are some delays. So what happens, this is a small possibility, but it actually happens, if one node in the network, okay, I need the board again. Okay, so what will happen if we have a couple of nodes in the network? They're connected. They're connected like this, okay, whatever. And we have this is a miner. They all are miners, let's say. And this miner, he mines a new block. He says, "Oh, I found a block. Let's call this block an X block." But this miner, in approximately the same time, he mines another block that is different block than this one, and we can call it epsilon block. Or better to use A and B, so you don't get confused by my writing. Okay, and A and B blocks. So this miner starts propagating his block, and this miner or a simple node just checks if this is the valid block, and it really is, and it extends it to the main chain. It says, okay, this is the valid chain now. So this is the end of the chain. This is the last current block, and it appends. It says, okay, this is now the last block. The last block is an A. But this miner believes that the last block is actually B. So when he propagates it here, this miner will tell, okay, last block is B. And when this last block B comes here, let's say they're propagating this way. And when this last block B comes here, this miner will check it, and he will see that it actually is a valid block, and he will also append it here. And he will say, okay, B might be the valid block, and this is the fork in the Bitcoin, so in the blockchain, actually. So for this, what happens now is that we have inconsistent state. We don't know which is a valid block. So if someone paid you a cup of coffee or anything, if someone paid you for a cup of coffee in Bitcoins, and this happened, you cannot be sure if this transaction will be valid in the future. So what network does, it reconverges in order to get to the single chain again. And how is this going to happen? Well, we will simply wait for another block, because the possibility of this mining, of this miner and this miner or any other miner to mine the block at approximately the same time, blocks are mined each 10 minutes in the blockchain, is very, very low. But it happens sometimes, but it rarely happens that after this, the same situation happens again for the next block. So when some miner mines the next block, let's say 10 minutes have passed, and this miner mines a C block. He says, okay, here is a C block. And he will propagate it. He will, because he has an A as the main chain appended, he will append a C block here. And if he is the only one that mined the block in this approximate time, he will distribute his block across all chain, and everyone in the chain will see that this C is valid block and it is appended to an A. And even those blocks will say, well, okay, we were wrong. B is not a valid block. A is a valid block. So they will come to this state as well, and B will be left with an. So if someone paid for your coffee by Bitcoins, and his transaction ended up here, he will get his money returned, and you won't get anything. So what people actually do, this is called I forgot to introduce you to the concept of confirmations. What is a confirmation? Basically, it's very simple. Confirmation is a number of, for this block, confirmation is number of blocks that comes after it. So this block has one confirmation. This block has 0 confirmations. There is no blocks after it, and this block has 2. So in order for you to be sure that this actual block is safe and your transaction is confirmed, you need to wait for at least 2 blocks, or for your transaction to actually have two confirmations, because there are 2 blocks after it, and you know that this possibility is very, very low. But what current systems do, they even wait a little bit longer. They wait for 6 blocks, and then you can be like 100% sure that this transaction is safe. So this is actually the concept of forks, because people usually ask, okay, there are numerous of nodes in this network, and if this node mines a block at the same time as this, it rarely does, but it happens. It can happen. The probability is low, but it won't happen that in the block sequentially happens that 6 times in a row, or even 2 times. It rarely happens that 2 times the same blocks. I never saw such a case. So you can really trust a transaction that has 6 confirmations. That's how we design our systems as well. So yeah, question. Oh, the mic. You can tell, and I will just repeat it. Oh, okay.
What actually happens with the transactions from the B? Are they repeated, or they are marked as invalid, or what actually happens?
They are marked as invalid, and those guys who sent their money in those transactions, they get their money back, because their money is not spent. Because here in the blockchain, you don't have, in the common bank systems, you have a concept of balance. Balance is an integer that tells you have 1 million something. But in the blockchain, there is no concept of balance. You only have transactions. That's how real money works. When I give you 100 euros, and that is a transaction. when you receive, give me back 20 euros or anything, that is another transaction. And we really, if you only have 100 euros, you can only give all of them this transaction. You cannot spend 20 euros out of this and not get a transaction back. So these transactions are actually just gave back because no one received them in the end. They are just invalid and people get their money back. That's why it's important for you to wait for several blocks, because otherwise, you know, she goes away with her cup of coffee and you don't get Bitcoin in the end, but she's already gone, 10 minutes have passed. So the fault is on you, actually. Yeah, there are more questions. Okay.
So I have a question and a follow-up question. It is my understanding that the miners can choose which transactions to put into a candidate block.
Oh yeah, but you can continue and then I will. Is that
Okay. Yeah. So I was wondering if that is the case, how come there aren't much more variations of candidate blocks that are broadcasted into the network if every miner can put together a different group of those transactions? How come they all don't disagree with each other, and so at any time there's a large number of forks in the blockchain? So
well, okay. First, okay, I will answer it immediately, and then I will explain something additionally. The miners, even if they can choose in the end what they put in their block. They do so by a greedy algorithm, which is no wonder. You know, they just check who has the most transaction fee, because I can say, okay, I want to send 1 Bitcoin, but this is so important to me that I will send half of Bitcoin as a transaction fee because I want my transaction to come first. And then miner will see, wow, I get half a Bitcoin for this guy's transaction. Of course, I will put it as the first one in my block. And this is actually the way the transactions are. It's just by transaction fee. They input the largest fees first, and then all other transactions. And if your transaction doesn't have any fee, you're a cheap bastard and you didn't have a fee, your transaction might not end in this block, but maybe it ends in the following one. Or if the network is so clogged right now, there are millions of transactions, your transaction might be in the block, in the 10 next blocks or something, so you will wait for like an hour or two for your transaction to actually go on the blockchain. So about your question, what if the miners put, it doesn't really matter. Even if they chose like two other transactions or anything, the first one who mines this block, it doesn't. The network isn't concerned about which transactions did it get. It is only concerned if this block is valid. So if the miner wants to put only one transaction in a block, he can actually do it, but and the network will be fine with it. But he will get only one transaction fee. And for him, it isn't faster to put one transaction in a block than more transactions, because for him the calculation of this, the making of this root Merkle tree is done even before he starts to actually mine. The mine is the hard process, the brute force. So whichever transactions are in this block, network isn't concerned by that. It is only concerned if this block is valid. If the miner can first mine the block. So if your question is if a miner can actually ignore your transaction if he knows that your transaction is...
That was not my concern. My concern was that there would be multiple ends of that blockchain because there are different blocks, and the block is only valid, as you said, once there are multiple blocks after it, right? The confirmation. But every next block, the hash of it is created using the hash of the previous block.
Yes.
So if there are multiple forks, like many of them, which are the miners going to decide of those to use?
It's just the miner. It depends on a luck. If the first block that the miner gets, the mine block, we saw here that this miner, for instance, he got an A block. It's just his luck. He will tell, okay, this first block that I got, I'm believing this is the transaction, the block that will end on the main chain, and he will believe it. If he gets any more blocks, B block, C block, whatever, he will say, For now, this is my side chain. I will put it aside. Maybe it is true, maybe not, but I got an A block first, and I will stick to it. Maybe I'm wrong, because like those nodes were. He cannot know it up front, because it all depends on luck. There is no way for him to know if this part of the network will mine the next block, or this part of the network. It is pure luck, as mining actually is.
And do you know how common that is, that a mined block is just thrown away?
These things that like with the one, let's call it the one layer of fork, can occur often, but there is like I've never even seen a tool like if here comes the C block and here comes the D block in the same time. I've never seen even this happen.
Okay.
And then for the 6 to happen, that never happened. That would actually broke many exchanges and whatnot, because they believe that after 6 blocks they can tell the customer, okay, yeah, you send us the bitcoins, everything is fine, we receive them. So
Thank you.
Yeah. So the next question.
Okay, my question is, as you said, miners, it takes some time to mine a block.
Yes.
So what if the miner is sending out failed blocks that spam the others, it takes some time to validate the block, but to fake the block, it's just easy. So he can send out many fake blocks and spoof the network, and take some time that he can count on his mining, and the others are validating nonsense.
Okay, yeah, that is true, but validating of a block takes actually even it is immediate. It is done by an O of 1. This is the complexity of validating a block. It's like when you get if someone tries to spam your network by sending you a GET request, basically.
Okay, so it's based on the protection that the network is so slow that the validating is so fast.
Yes,
Yeah.
exactly.
Okay.
Exactly. That's the whole point, because when someone sends you a hash and he says, this is the nonce that I use to create this hash, you can immediately, in this complexity, you can see if he is lying or not. But for him, in order to get to this nonce, if he wants his block to be valid, he needs to spend significant effort. This effort is this brute force that we just showed. And for him to do this is his proof of work. This is him throwing the dices in front of us, and we are seeing if he throw 12, and we can assume, of course, miner can get lucky. You know what I mean? Not lucky that you mine with nonce of 0 and you get magically your hash, but you can do it sometimes faster, sometimes slower. But on average, you will need certain amount of times, and this amount of times for the dices are 30 something, and I'm not sure which is for the current difficulty of Bitcoin.
Okay, are there any protection system within Bitcoin that are against spoofing the network and slowing down the others, or it's just open to anyone and everything is validated?
No. As far as I know, there is not. And the one more interesting thing about Bitcoin network is that it doesn't even encrypt its data when it is communicating with each other, because this network is perfectly secure. That's the beauty of it. Actually, you can see everything. Once I create a transaction, I can show it to everyone, and everyone can validate that this is my transaction, that I'm spending money, but no one can take away my money because I'm holding it with my private key. This introduces a single point of failure, because if the user has all the power, if I show to anyone, even for a second, my private key, and he's able to take it away, he is immediately the owner of my keys, and he can immediately spend my Bitcoin. So, and because in the current system, you know, if you're trying to hack someone's credit card or something, it will take you time for a bank to transfer the money, and you won't be able to take away all his money because banks have protection for that. But in the Bitcoin, if you are not a smart user, you can get your money stolen. This happens all the time. But if you are a smart user, this network is bulletproof, actually. Okay, next question. You can just tell me and I will repeat the question if it's easier for you. Okay.
How it work?
Yeah.
Yeah, my question was about the 10 minutes for making one block.
Okay.
Mining. As I understand, it's like a combination of current computation power of all the mining network and specification of target. Is it right?
Yes, yes.
So this is like a decision by the, I would say, like the whole community to have 10-minute target.
Yes.
So it doesn't look like really like day-to-day spending currency, because if I want to buy coffee somewhere, I do not want to wait 1 hour to validate the transaction. So is it like the decision, like the design decision, that this is not for these fast transactions?
Well, yeah, it is. I mean, you could, if you are trusting the network, you could immediately trust a transaction. Like, let's say, you know how those credit cards work that doesn't require your PIN, but if you're spending something that, let's say, less than $100, it will immediately pass your transaction. Well, the bank actually doesn't know if you have the money or not, but it is saying, okay, this is a client of mine, and I trust him that he has $30 or $10 for a cup of coffee. It won't make me go bankrupt. I'm believing him in advance, so your transaction can pass like this, and then they will check it later. And if they know that you cheated on them, then they will, like, I don't know, ban your account or something. So if you are building a system and you are selling something for $1, you don't really need to check, like, let's say, you can believe the network and set the difficulty to, like, you can immediately trust a transaction like after one block, and you can believe that this has passed, and you don't need to check if there are 6 confirmations or something. But if you want to transfer a larger sum of money, then it is better to actually validate, because here there is also the next good thing about this system is that you can send any amount of money over the network straight to some other person. Like, let's say I want to send $1 million to someone in Japan. If I wanted to do this in any way, even if with cash, I will need to fly there and give him a purse. But if I wanted to go over a bank or anyone else, there will be complicated procedures, and it would take several days at least. But with Bitcoin, you can do it immediately after those 6 blocks. After like 1 hour has passed, he would get all his money, and you, if the network isn't clogged at the moment, you can even go away with a 0 transaction fee. So you send $1 million and you don't pay a transaction fee. But if you want to send $1 million over the bank, you would need to spend a large amount of money for the fee, actually. So it only depends. It purely depends. It's also a bad thing if you want to send a small transaction and the network is clogged right now. And the Bitcoin actually has a problem with this, and it tries to solve it with the Lightning Network, segregated witness, but that's not included in this presentation. It used to take me like half an hour more to explain, probably. So it isn't perfect yet. Of course, you cannot. If you're asking me if I can, be 100% sure that this transaction is valid, then if it can pass like 30 seconds are passed, then no, you cannot do that. But this is a good example for what Bitcoin can be used. There is also one more thing. If you're asking yourselves why 10 minutes, well, nothing changes if you really take this amount of time and lower it to like 1 minute or 1 second, whatever. Then you wouldn't need 6 confirmations, because the computation power in it to break those 6 confirmations would be a lot less. So you would actually need, I don't know, several hundreds of confirmations, and you will, in the end, come to the same amount of time. So the 10 minutes is just something that was defined in the beginning when the Bitcoin was created, and they stick to it for now, at least.
So in the end, it's like the like acceptable limit for society, for trust in the transaction. Yes. Thank you.
I have a question.
Yeah.
The first one that mines the block gets the 12.
Yeah, and a half.
And it's immediately put in the blockchain, or?
Yes. Well, he immediately, it is put in the blockchain that he gets this money, but he cannot spend it in the next 100 blocks. That's for a miner. He gets these bitcoins, but he cannot. This is a safe safe way for a miner not to cheat, because if the miners find a way to break this, they would need to wait for a long time before they can actually spend their new mined coins.
And let's say what happens if there's no one, like the nonce is that long, like the streak of the zeros is so that long that nobody manages to mine the block in 10 minutes. What would happen then?
Okay, good question. The blocks, when I say the blocks come in 10 minutes, it's on average on 10 minutes. Because the block can actually sometimes, because this is a lottery, you are mining, you're brute forcing it, sometimes it happens for 6 minutes, 5 minutes, 1 minute if they're lucky. Sometimes if the network computation power is good, sometimes it happens later, like 11, 12 minutes. But what the network does is this target is actually recalculated by the network after like 2016 blocks have passed. This target network will look at the past, because computation power changes. Bitcoin was invented in 2009. Computation power of I don't know, graphic card was a lot less than what it is now. So they had this in mind. So they implemented it in a way for the network to check 2016 blocks previous, and they compare it to the time that it would take it, like 20,160 minutes. And if it is lower or higher, they increase or decrease the difficulty. Because if network, for some instance, I have a huge mining farm and everything burns down or something, then, well, I'm sad, but the network also, the computation power lowers. So we need also to lower the difficulty of the mining, because we want our blocks at 10 minutes. So that's a way for network to readjust the target and the difficulty by it. So any other questions?
The last question.
Okay, just 1 second. Previously, I just want to show you about the. You see our block took 3 seconds, so we can just start it with the 7 zeros, and we can continue to a question. Okay. Yeah.
Okay, so I would like to ask if the miner can choose the transactions to put in the block.
Okay.
How it is prevented that one transaction will not be in 2 blocks?
Well, because while they are mining it, while there are multiple candidate blocks in this network. If everyone is mining, there will be like 7 candidate blocks. But the first one who mines it and relays it to the network, this is the valid block. As soon as this miner gets that his block containing some transactions is mined, he will say, okay, I give up on my mining, I lost the battle, I lost the race. I will start with the new blocks, with the new unconfirmed transactions, because if he mines a block that contains already a transaction, the network will see this is not a valid block, because this transaction is already spent before. So there is no way for a miner to mine the same transaction in 2 blocks.
So the network checks the transactions.
Yeah, exactly.
Okay, thank you.
Okay. So for the last part, I just want for you to recommend you a book. This is a book I learned from a lot. So it's by Andreas Antonopoulos. It's called Mastering Bitcoin. And this is, I recommend that you read the latest 2nd edition, because it has covered, it has this Lightning Network and segregated witness covered. Some of you probably heard about it because it was on the, I don't know, media and stuff. So check out this book if you want. At least if you're not a technical person but wants to know how it works, you can check out first 3 chapters and they cover everything, and later he goes into details. So, and that's it.
So thank you.
Thank you.